Hello and welcome back. Today we will continue our discussion of LTI systems in Lecture 2-2. The objectives of today's lecture are to find the frequency response for an LTI system given the impulse response and to find the output of an LTI system given an arbitrary input. Example 1. Find the frequency response h of j omega for the impulse response h of t equals e to the minus t u of t. But before we jump into solving this problem, I want to relate this back to what you studied in your circuits course and how to actually find the impulse response. So here we have an RC circuit with an input x of t and an output y of t. There are several ways to do this, but we're going to do it using phasor analysis or Laplace analysis. So if we were doing Laplace analysis, we would rewrite the capacitor as 1 over SC. Or if we were doing phasor analysis, we would rewrite the capacitor impedance as 1 over j omega c. Remember, we talked about before that S is equal to j omega for sinusoidal steady state. So the transfer function using Laplace analysis, h of s would be equal to 1 over SC divided by r plus 1 over SC, or we could write this as 1 over RC divided by S plus 1 over RC, and then we would find the impulse response h of t by finding the inverse Laplace transform of 1 over RC, S plus 1 over RC, which gives us 1 over RC, e to the negative t over RC, u of t. So that's the impulse response. And then if r is equal to c, which equals 1, we end up with h of t equals e to the minus t u of t, which was in our problem statement. We could also do the same thing to find h of j omega, where h of j omega, our impulse response, would be 1 over j omega c divided by r plus 1 over j omega c, which can be rewritten as 1 over 1 plus j omega RC, where tau equals RC. That's our time constant, which would be 1 second. So hopefully you can now see how our impulse response and our transfer function and our frequency response are all related. So now back to example 1. So h of j omega is equal to the integral from minus infinity to infinity h of tau e to the negative j omega tau d tau, which equals the integral from minus infinity to infinity e to the negative tau e to the negative j omega tau u of tau d tau, so that u of tau changes our limits of integration to be from 0 to infinity e to the negative tau e to the negative j omega tau d tau, which equals the integral from 0 to infinity e to the negative quantity 1 plus j omega tau d tau, which is equal to negative 1 over 1 plus j omega e to the negative quantity 1 plus j omega tau evaluated from 0 to infinity, which equals 1 over 1 plus j omega. So now that means that the magnitude of h of j omega is equal to 1 over the square root of 1 plus omega squared, and the angle for h of j omega is negative the arctangent of omega. So we've already talked about that if h of t is real, then h of j omega should demonstrate conjugate symmetry. So what that should mean is that the magnitude of h of j omega should have even symmetry, which we can see here. It does, where the maximum value is 1 at 0, and it's negative 1. At negative 1, And at positive 1, the value is 1 over the square root of 2. Something we're going to talk about later is that this circuit, that RC circuit that I showed earlier, as well as this sketch, represents a low-pass filter. This is a low-pass filter where at omega is equal to 1 and negative 1 would be called the half power point or the cutoff frequency. So omega C, or the cutoff frequency, would be 1 radian per second. And you should note here that this is equivalent to 1 over tau, or 1 over the time constant. So here we have a low-pass filter, which means it passes low frequencies, and as the frequency increases, the magnitude dies off. And the phase angle, negative the arctangent of omega, looks like the following, where the angle is actually 0 at 0. Remember, this is the angle, h of j omega, and this was the magnitude, h of j omega. And at that cutoff frequency, negative 1 and 1 again, the angle for negative 1 is 45 degrees, and for 1, it is negative 45 degrees. And the asymptote, as omega goes towards infinity, is positive infinity. It's approaching negative 90 degrees. And for negative infinity, this curve is approaching positive 90 degrees. So this is the general shape for the magnitude and phase for a low-pass filter, and also for a system that demonstrates Hermitian symmetry. Example 2. Find the output y of t for a system with h of t equals e to the minus t u of t and x of t equals 5 e to the j 2 pi t plus 30 degrees. So once again, what's going to happen here is x of t is going to be passing through our low-pass filter, and we want to find y of t. So thinking about this in terms of our system, we now have this system in the frequency domain where the input is going to be 5 e to the j 2 pi t plus 30 degrees. And it's going to pass through a system with h of j omega equals 1 over 1 plus j omega. And I'm trying to find the output y of j omega, which is going to equal h of j omega times x of j omega. So omega naught is equal to 2 pi, and theta is equal to 30 degrees. So I can rewrite my input as 5 e to the j 30 degrees times e to the j omega naught t, thinking about our basic signal that we talked about in a prior lecture. And my output would be h of j omega naught e to the j omega naught t. So I'm going to evaluate my frequency response, h of j omega, at omega naught equal to 2 pi. So h of j 2 pi is equal to 1 over 1 plus j 2 pi, which is equal to 0.157 e to the negative j 81 degrees. Very similar to what you did when you did phasor analysis before. And rewriting the input x of j 2 pi as a function of its magnitude and phase, that's 5 e to the j 30 degrees. So just like when we did phasor analysis, we know that the frequency remains the same, so our phasors just hold magnitude and phase information, and we can put the frequency back at the end. So y of j 2 pi is going to equal 5 times 0.157. So you multiply the magnitudes together, e to the j, and then you're going to add the angles. So that's going to be 30 degrees minus 81 degrees. So y of j omega is 0.785 e to the negative j 51 degrees. I can also write it as y of t equals 0.785 e to the j, and now I bring my frequency back, 2 pi t minus 51 degrees. You can use spectrums to represent the magnitude and phase information in a signal. So we're going to plot this for the input, the filter, and the output. So the magnitude of x of j omega, we would show that it has a frequency component with a magnitude of 5 at 2 pi. And for the angle x of j omega, we're going to have 2 pi has a phase angle of 30 degrees. So then we're going to once again make the sketch of the low pass filter, h of j omega. So here's our sketch from the previous problem, but really the only value on here we care about is the same frequency where the input is. So here at 2 pi, we would show that it has a value of 0.157. And the phase angle for the low pass filter, h of j omega, we would show here at 2 pi, it has a value of negative 81 degrees. And then finally, we plot the magnitude and phase spectrum for y of j omega. So for the magnitude of y of j omega, we're going to have at 2 pi a value of 0.785. And for the angle of y of j omega at 2 pi, we're going to have a value of negative 51 degrees. Example 3. Find the output y of t for a system with h of t equals e to the minus t u of t and x of t equals 5 cosine 2 pi t plus 30 degrees. The way you would have done this problem in AC circuits would have been to find the phasor equivalent for x of t, and then you would have solved for y of t by doing the following. Y of t is equal to the magnitude of x times the magnitude of h of j 2 pi times the cosine of 2 pi t plus the angle for x plus the angle for h of j 2 pi. So we're going to see another way to solve this problem, but you end up with the similar result. So the first thing we're going to do is use Euler's identity to rewrite x of t as 5 halves e to the j 2 pi t plus 30 degrees plus 5 halves e to the negative j 2 pi t plus 30 degrees. And y of t is going to equal 5 halves h of j 2 pi e to the j 2 pi t plus 30 degrees plus 5 halves h of negative j 2 pi e to the negative j 2 pi t plus 30 degrees. Now we know h of t is real, so h of j omega has Hermitian symmetry. So because of that, we know that h of negative j 2 pi equals h conjugate of j 2 pi. So we can rewrite y of t as y of t equals 5 halves h of j 2 pi e to the j 2 pi t plus 30 degrees plus 5 halves h conjugate of j 2 pi e to the negative j 2 pi t plus 30 degrees. So we can rewrite this as y of t is equal to 5/2 times the magnitude of h of j 2 pi times e to the j times the angle h of j 2 pi times e to the j 2 pi t plus 30 degrees plus 5/2 times the magnitude, and remember this is even symmetry, so I can write h of j 2 pi again, e to the negative j, the angle h of j 2 pi, e to the negative j 2 pi t plus 30 degrees. By using algebra, I can rearrange and write this equation as 5 times the magnitude of h of j 2 pi times the quantity e to the j 2 pi t plus the angle h of j 2 pi plus 30 degrees plus e to the negative j 2 pi t plus the angle h of j 2 pi plus 30 degrees divided by 2. So what you should see here is that this part in the bracket is Euler's identity for a cosine. So we can rewrite this as 5 times the magnitude of h of j 2 pi times the cosine of 2 pi t plus the angle h of j 2 pi plus 30 degrees. Hopefully this is starting to look familiar to you, to like what you did when you did phasor analysis before. So this ends up being 5 times 0.157. We found that in the previous problem. Cosine of 2 pi t plus 30 degrees minus 80 degrees. 81 degrees. We also found that in the previous problem. So this ends up being 0.785 cosine of 2 pi t minus 51 degrees, which you would have also gotten from phasor analysis. So the response to a sinusoid to an LTI system must be a sinusoid at the same frequency, although the magnitude and the phase may be different. So now I'm going to rewrite y of t by using Euler's identity so that I can make the magnitude and the phase spectrum, so we can take a look at those. So what we have here is that y of t is equal to 1/2 times 0.785 e to the j 2 pi t minus 51 degrees plus 1/2 times 0.785 e to the negative j 2 pi t minus 51 degrees. So first, the magnitude of x of j omega and the phase for x of j omega are going to have two frequency components. One at negative 2 pi, one at positive 2 pi, and both of them have values of 5/2. There are also two angles, one at negative 2 pi and one at positive 2 pi. The one at negative 2 pi has a value of negative 30 degrees. And the one at positive 2 pi has a value of 30 degrees. Notice that x of j omega also has conjugate symmetry. Then the low pass filter, the magnitude of h of j omega evaluated at 2 pi and negative 2 pi gives us values at 0.157 for both. The angle for h of j omega has values at 2 pi and negative 2 pi. So at 2 pi, that's going to have a value of negative 81 degrees. And at negative 2 pi, it's going to have a value of positive 81 degrees. And then we're going to do the magnitude of y of j omega. The magnitude of y of j omega also has two values at 2 pi and negative 2 pi. And for both of those, its value is 1/2 times 0.785. And the angle for y of j omega is going to have two values, one at 2 pi, which is negative 51 degrees, and one at negative 2 pi, which is positive 51 degrees. And this concludes example 3. Example 4. Find the output y of t for a system with h of t equals e to the minus t u of t, and x of t equals 3 plus 7 cosine pi t minus 45 degrees, plus 5 cosine 2 pi t plus 30 degrees. Notice we can think about this problem like superposition, where x of t is equal to x0 of t plus x1 of t plus x2 of t, and our output y of t is going to be y0 of t plus y1 of t plus y2 of t, where we're finding the output due to each of these inputs and then adding them together. You did something very similar when you did phasor analysis, because you now have inputs at 3 different frequencies, so you could not sum the phasors together, but in the time domain, you could show the sums of each of the outputs at the different frequencies. So first, we'll rewrite x of t as x of t is equal to 3 plus 7/2 times the quantity e to the j pi t minus 45 degrees plus e to the negative j pi t minus 45 degrees plus 5/2 times the quantity e to the j 2 pi t plus 30 degrees plus e to the negative j 2 pi t plus 30 degrees. So y of t is equal to 3 times h of j0 plus 7/2 times h of j pi times the quantity e to the j pi t minus 45 degrees plus e to the minus j pi t minus 45 degrees plus 5/2 times h of j 2 pi times e to the j 2 pi t plus 30 degrees plus e to the negative j 2 pi t plus 30 degrees. So now let's evaluate our filter at each of our frequencies. At DC, or h of j0, our filter is 1 angle 0 degrees. At h of j pi, our filter has a magnitude of 0.303 and an angle of negative 72 degrees. And at h of j2 pi, we have found from the prior two examples that the magnitude is 0.157 and the angle is negative 81 degrees. So now we can write y of t as 3 times 1, and we know that it'll have an angle of 0, so I can just write that as e to the j 0 degrees, plus we will have 7/2 times 0.303 times the quantity e to the j pi t minus 45 degrees minus 72 degrees plus e to the negative j pi t minus 45 degrees minus 72 degrees plus 5/2 times 0.157 times the quantity e to the j 2 pi t 30 degrees minus 81 degrees plus e to the negative j 2 pi t plus 30 degrees minus 81 degrees. And finally, simplifying, we have that y of t is equal to 3 plus 2.12 times the quantity e to the j pi t minus 117 degrees plus e to the minus j pi t minus 117 degrees divided by 2 plus 0.785 times the quantity e to the j 2 pi t minus 51 degrees plus e to the minus j 2 pi t minus 51 degrees divided by 2. So using Euler's identity to rewrite this as a cosine, y of t becomes 3 plus 2.12 cosine of pi t minus 117 degrees plus 0.785 cosine 2 pi t minus 51 degrees. So once again, we see that this ends up being y0 of t plus y1 of t plus y2 of t using superposition. Finally, I'm going to plot the magnitude spectrum for y of j omega and the phase spectrum for y of j omega. I will leave it to the viewer to make the spectrum for the input and the frequency response. So for the magnitude of y of j omega, what you're going to have is at 0, a value of 3. So you see the DC value passes through with no changes to the magnitude of the phase because it's a low pass filter and that's at the lowest frequency you can have. And at pi, we're going to have values of 2.12 divided by 2. And at negative pi, we're going to have 2.12 divided by 2. And at 2 pi, we're going to have a value of 0.785 divided by 2. And at negative 2 pi, we'll have a value of 0.785 divided by 2. So then for the angle, y of j omega, we are going to have at 0, 0 degrees, and at pi, we're going to have negative 117 degrees, and at 2 pi, negative 51 degrees. At negative pi, we're going to have a value of 117 degrees. And at negative 2 pi, we'll have a value of positive 51 degrees. And this concludes Lecture 2-2 on linear time invariant systems.